Now is it audible? Okay, yes it is. That's fine. Okay, so I don't know if this works with this. Let's see, because I seem to have misplaced my, this is mine. I seem to have misplaced my dongle. That's okay, I think it should be fine. Yeah. All right, good morning. So today I guess you've had a couple of talks on broadly big data, am I correct? So I think you had probably one on machine learning, maybe one on big data and testing, right? So today I'll talk a bit more on systems, right? Essentially what kinds of big data platforms and systems are out there to help you deal with data at large, right? So most of you have heard of MapReduce. Just a show of hands, how many of you guys have heard of MapReduce? Okay, that's about a third of the class, right? So how many of you have used MapReduce? Okay, a couple of you guys. So even you guys will benefit. There's a bunch of stuff other than MapReduce also, but we will also go into MapReduce briefly. So I'm just going to sort of give my own definition of what big data is, because it's often used and abused in various ways. So I mean, I work on broadly distributed systems, large-scale systems, and so on, right? And to me, the problem is fairly simple, right? Anything you can't do with things you already have is big, right? It's too big to manage. So data which challenge traditional data collection, processing, and management techniques is effectively big data, which is almost like saying that something I can't solve today is big data. I can solve it today, and I go on to something else tomorrow, which I can't solve tomorrow, right? So it could be because of a lot of interconnectedness. It could be because of, for example, things like Internet of Things. That's a big hyped up term, right? So and with things like IoT or Internet of Things, you have lots of these devices that are coming online, be they things like smartphones or sort of Fitbit kind of personal devices or smart meters and so on. And all of these are connected to the internet pretty much all the time, and they're constantly generating data, right? So you have a lot of streams of data coming from all these various devices. So that's one type of big data. Another type is from all the social media that everyone is sort of connected through in terms of whether it be tweets, Facebook posts, pictures, and all those things. And then you also have sort of mobile devices themselves being very pervasive, and not just as a means for sort of making phone calls, because you probably spend a very small fraction of the time actually using the smartphone as a phone, right? Most of the time is actually spent doing things besides speaking on the phone, right? So that, along with the advent of sort of cloud computing at large, has made sort of it possible to both collect and process big data. And lastly, there's a lot of interesting algorithmic work also, some of which you might have heard earlier on in the summer school, and algorithms and analysis techniques that are possible to manage from a formal perspective a lot of these big data sets, right? So let me give you a few examples of what I see as some interesting big data data sets, right? So we may not think of science as being a big source of big data, but oftentimes science or scientific domains have dealt with larger data sets than enterprises have at specific points in time. And this is an example of astronomy, which is fairly benign science. It's not very exciting like, I don't know, nuclear physics or something like that. But even things like astronomy, they have actually been dealing with large-scale data sets. And this is an example of a sky survey. And so nowadays, astronomers don't have these telescopes that they point at the sky. They actually have digital telescopes or radio telescopes, which are huge, right? These have things like gigapixel cameras, right? Not your megapixel cameras that you have. These are digital cameras that scan the sky, right? They don't look at specific stars. They scan the entire sky, and they essentially say, let's get all the data, right? And then in the leisure of your desktop, you can actually go and zoom in virtually into different parts of the sky, right? So capture everything, and when you want to, go digitally and look at specific parts of the sky, right? And these kinds of sky surveys collect petabytes of data on a periodic basis, right? And that's petabyte is still something that we can't grapple with, let's say, in your house, right? You can deal with terabytes of data with a couple of hard disks, but petabyte is still less common, right? And this is happening right now, or it's been happening for the last couple of years. I think China's radio telescope was in the news also the last couple of days, for those who noticed that. So these are sort of large sort of surveys telescopes that capture a lot of data. Next-gen sequencing, that's been in the news for the last few years, where you can actually give a drop of blood and have your entire genome sequenced for a couple of $1,000. These generate terabytes of data per person. If you think about these becoming clinical, which means that in a couple of years, if you go, you sort of, a doctor wants to diagnose you. Instead of just taking a blood draw and doing some sort of chemical study on that, they might do a blood draw and do a genome study, right? And there you're looking at terabytes of data per person, and at a hospital like, let's say, MS Ramaya next door, you might be seeing terabytes of data per day being collected. And you have to analyze it within a few hours because you can't sort of wait for a week or two to actually get a clinical result, right? And likewise, Large Hadron Collider, that's been in the news for the boson and all those things, that again has been generating petabytes of data for the last couple of years. So science has actually been dealing with big data for many years now, right? And more familiar examples, social network, Facebook being a great example of that. You've seen exponential growth in the number of people who are part of Facebook. And it's not just the growth of the network itself, but it's the richness of the content, right? Because many years back, Facebook just allowed you to do a wall post, right? But then they came with pictures, right? Then you can actually put news clips and it'll sort of show a small blurb. Then you could do instant messaging. And now you have things like FaceTime, right? So you have a bunch of these, both the richness of data has been growing and the size of the network itself has been growing also, right? And meaning one of the cool features they brought in a couple of years back was sort of face recognition, right? So they could actually, if you upload a photo, they'd actually recognize pictures of your friends and actually tag it automatically, right? And that, you can bet, took several years of research to get to such a point, right? So it's not just the size of data, but complexity of data that's been increasing also. And just to give an example from governance, right? Because that's again one less appreciated part of big data. Aadhaar is one of the sort of poster childs for big data, I would say, in India, right? And it's got the largest biometric database in the world. It's 3 times larger than the next biggest database, which is the US visa processing system. So those who are going to the US for your visas and all those things, you'll actually give your fingerprints. So that's the next biggest database at 1/3 the size. We have about 1 billion or so in our database. And this is being constantly used. So every day they process about 1 million or so people, even right now, as they sort of bring the entire country on board. So these are million pictures, digital prints, iris scans that are being processed on a daily basis as we go forward. And it's not just the data collection, but it's also the authentication, which is going to start coming in gradually, right? So when you go and sort of give your fingerprint and you want to authenticate yourself, let's say to come into a door or come into a conference room, right? So that has to be instantaneous. So if you go to a bank and sort of want to do your KYC or something like that, using your fingerprint on your Aadhaar, that has to be instantaneous, right? So you're looking at thousands of transactions per second that have to happen in a sort of, with a low latency kind of model as we look at such large scale government data sets. So just to sort of point out one feature over here. So this, let's see if I can get my pointer visible. Okay, just look at the plot on the right side, right? So you actually see the x-axis is the time of the day. The y-axis is the number of packets that are seen during that interval. And this is for the data collection part when they're originally enrolling people. And here you'll essentially clearly see a sort of bimodal distribution, right? So, and this is natural in terms of human behavior, right? So the first peak is for the morning. So the morning session, people come, give their biometrics, and they're sort of loaded. And then there's lunchtime, and then where there's a dip, and then there's another peak over here, right? And while I don't have it here, if you look at authentication right now for Aadhaar, one of the key users is actually the government, central government employees. So most of the offices, they actually have to sort of give their fingerprint when they come in and go out so that the government knows that they're at least warming their seats for an 8-hour period, right? So there again, you'll actually see a peak at maybe around 9 a.m. and maybe another peak at 6 a.m. in terms of the authentications that are taking place, right? So more broadly, big data has sort of been classified into sort of what are called these 4 V's, right? Again, this is just a mnemonic. It doesn't really a sort of formal way of looking at characteristic of big data, but it's a useful rule of thumb, right? So you got things like volume, where you look at just the sheer size of data. For example, the petabytes of data from the SKY survey. It's not like you have to go and look at every pixel in the entire image. You essentially do some image processing on the image and get a series of synthesized data sets on which you actually do science or astronomy and so on, right? But dealing with the sheer scale of data in terms of bytes itself becomes challenging, right? So that's volume, right? And you have velocity, which comes in the need for doing more low latency processing, right? So while you might have this astronomy data that you collect, but you might choose to sort of analyze it over several days or weeks, low latency processing, such as the Aadhaar authentication or things like sort of Internet of Things, these have to be processed as they come in because A, the user requires a response immediately, and B, the volume is so much that you can't afford to keep it because it's not like if you buffer it, the volume is going to subside and you can leisurely process it. You're literally drinking from a sort of big water tanker. So you either drink it or you overflow, right? So velocity is one other dimension. Variety is just the different types of variations. So in classic relational databases, you have a very neatly laid out table, right? So you've got columns, you've got rows, you've got tuples, you've got relational algebra. All of that is very structured, very easy to handle, right? But when you're dealing with tweets, right, which are sort of not even good English, it's just arbitrary English, and you're dealing with images and video, when you're dealing with data from sort of sensors, right, some of these don't necessarily have a lot of structure to that, and they might also have different types of analysis that you might want to do to actually get structure out and actually make sense of what the data is trying to sort of tell you. And lastly, there's veracity. Just because you have a lot of data doesn't mean it's actually meaningful data, or you can actually you can rely on the quality of data, right? So you need to, so for example, something like a Fitbit, which essentially tells me what my heart rate is, what my activities and so on, might be great for me to sort of just as out of curiosity know what my activity levels are. But this is not something that a doctor could use for their diagnosis in case when they're doing a surgery or something like that. The kinds of equipment that you have for doing the same kind of measurements are vastly different, right? And one of the things in terms of the hardware is in terms of the accuracy that hardware can give you. But likewise, in terms of software, there are different algorithms that you can use. Some of them might be deterministic algorithms that give you high accuracy. Others may be non-deterministic. So knowing how the data is generated and what kinds of analysis you're performing on them is going to be very crucial depending on how you're using the outcome of that, right? So veracity or sort of uncertainty or certainty in data and being able to quantify that becomes fairly important, right? So that's sort of the big picture on what the big data opportunities or sort of the sources are and what we might want to do with that, some use cases, right? But how do you really, let's say you've come up with a very nice technique for analyzing data, right? But this technique is highly complex, right? So, and you got maybe a couple of terabytes of data that doesn't fit in your local laptop, right? So how do you actually process this? How do you take your analysis techniques and apply it at scale, at large scale, on top of big data to make sure that you actually get results in a reasonable amount of time, right? So big data platforms help you acquire, manage, and process large-scale data sets at massive scales using distributed resources such as commodity clusters or cloud or even things like accelerators like GPUs in order to meet your application needs. So that's sort of the big context for what these big data platforms give you. And typically when you talk about platforms, we're talking about a couple of things. So one is what's the programming model that you use for accessing the platform, and the other is actual hardware on which these programs run, right? So we'll be talking about both of these in the next half hour or so, right? So talking briefly on the hardware itself, right? One of the hardware infrastructure of choice for such big data analysis has become cloud computing or cloud data centers, right? So here, this is in contrast to HPC or high performance computing clusters. For example, if you guys visit SERC, that's across the street over there, that actually has India's fastest supercomputer, right? Sahastra, that runs at a petaflop speed, right? But you only have one of those in India at that speed, and you don't really want to take, let's say, medium-sized problem and run it at that, or let alone small-sized problem, right? So the accessibility of high-end hardware is fairly low. This is worldwide, not just in India, right? So which means that, and it's fairly difficult to buy your own cluster, not just because of the cost, but because of management, right? So you need to have a sysadmin, you need to make sure all the software is up to date, you need to make sure there's UPS connectivity, cooling, all those things. So it's very tedious to manage your own data center, but you do need access to such resources. So cloud data centers allow you to rent virtual machines that's given by service providers like Amazon or Microsoft or Google and so on. And they take care of the management of the data center. They buy thousands of servers. They take care of the cooling, management, power, and all those things. and they allow you to rent it by the hour. So you could go and let's say rent maybe 100 CPU cores for maybe about 30 rupees an hour, right? Or 300 rupees an hour. And you use it for however much duration you want to, and then you give it back, right? And 300 rupees is maybe a couple of cafe coffee day visits, right? Or maybe one, depending on how the size of the group. So this is an example of one of these data centers. They're sort of massive, right? These are the size of maybe you could fit one in maybe a couple of them maybe in a cricket stadium. They're huge. They have cooling on the roof and so on, and they're highly secure. So and these are kinds of racks that you'll find over there. So these are sort of cloud data centers where you typically run your big data applications, right? So when we talk about systems, right, we're going to be talking about a few things. Big data platforms are scalable systems, right? So one is we're going to be thinking, you need to start thinking about it in terms of stacks, right? Just like you have, for those of you who have taken a networking course, you have the OSI or the sort of the 5-layer stack and so on, right? So there's really layers of abstraction, right? So even within your operating system, if you want to use your hard disk, you don't go and actually write blocks or let alone flip electrons in a disk directly, right? You go through your file system, the file system converts it into blocks, the blocks get converted to whatever the hard disk can understand, and then you write it. So these are different layers of abstraction that you build for most things in computer science, right? So if you write a program, you're writing it in C or Java, you're not writing it directly in assembly, right? So that's sort of the distinction over here. So likewise in big data, these platforms themselves are layered in terms of stack, right? And we'll talk about a couple of these stacks today. And Hadoop itself, or Hadoop MapReduce itself, is one of these stacks that's become very, very popular, right? So the other is sort of understanding the data characteristics, right? The volume, velocity, variety were one type of characteristic, but for broad classification. But even within that, let's say you're doing stream processing, just knowing that the distribution is bimodal can help you actually plan for things. If you know that you're going to have a morning peak and an evening peak, you can plan, let's say, your scheduling such that you have adequate resources during those periods of times, right? So understanding the data characteristics more deeply is very important when you start using these platforms. And lastly, understanding what infrastructure you're running it on, right? If you're running it on cloud, it has some properties. If you're running it on HPC machines, it has certain properties. If you're running it in your laptop, that has certain restrictions. Or if you're running it in a mobile phone, those have different kinds of capabilities, right? So making sure that you pick the right platform and the right algorithm to run on the right underlying infrastructure is fairly important, right? So today we'll talk primarily about programming models and some of these programming platforms. The programming models essentially make it easier for you to write distributed applications, right? And essentially make use of the underlying hardware, which itself can be fairly distributed and complex, and allow you to develop distributed algorithms and analytics using these programming models, right? And lastly, sort of once you sort of map it onto the programming platform and underlying hardware, you do need to do some tuning, so it's not going to run out of the box. So you have to do some kind of optimization. This is again something that you'll have to think about, right? So I won't go too deeply into the last two aspects because we don't have time. But we will talk a little bit about some of the programming models over the next few slides, right? So first we'll talk about data volume and MapReduce because that's one of the most popular stacks out there. So MapReduce is about 12 years old right now, right? And it's become so popular that it should literally be something that's taught in every undergraduate curriculum, just like they might teach C or Java. And MapReduce is essentially a sort of programming model or a programming abstraction, or as they call interface, for doing automatic parallelization of your application. Once you write it in MapReduce, the application is by default parallelized. You don't have to think about parallelization as long as you follow the programming model primitives, right? And for working on a distributed environment for large-scale computation. So if you actually take MapReduce, we write a MapReduce application and give it a very small data set, I can bet you that it's going to run 100 times slower than writing a sort of shared memory algorithm in C and running it in your laptop, right? Because it's not designed for small-scale data sets. So if an application can run on a single machine, if it can run in your laptop, you shouldn't be using MapReduce, right? But if you can't fit in your laptop, or if it can't fit in a single server, and you actually need to use many machines because the application is complex or the data is too large, then MapReduce is a good option to think about, right? And this is combined with an implementation of this that achieves high performance on a large cluster of commodity machines, right? So commodity machines is important in the sense that when you talk about commodity, we mean that the reliability of these machines is not really, really high, right? So, for example, a standard PC, if you're running it 24/7, it'll probably fail once a year or a couple of times a year. Your hard disk might go out, maybe your memory might fail, and so on. On the other hand, high-end servers, these might fail maybe once every few years, right? And really advanced machines might not even fail in a decade because they are used for really mission-critical applications, right? So MapReduce is meant for commodity PCs and cloud VMs in the sense that they don't expect a high degree of performance and reliability, and some of this performance and reliability is built into the programming model rather than relying on the hardware, right? So MapReduce itself, essentially, the original intent for Google coming out with MapReduce was to essentially analyze their web logs. So they used to do a web crawl of the entire web, collect the data. They wanted to sort of build search algorithms and ranking algorithms on top of that. And they quickly realized that writing custom applications, C or whatever, Java applications, was not really cutting it. So they actually came up with a programming model which could actually distribute this workload across a set of machines. It's designed for slow networks, slow in the sense that we are looking at Ethernet, not high-performance network like InfiniBand and MyRenet, which most of you guys might not have even encountered. So it's for traditional Ethernet. It's designed to scale out, meaning that there's this notion of weak scaling in computer systems, which says that as you increase the size of the problem, let's say the input data set, and correspondingly increase the number of machines available to the problem, the total time taken should be constant, which means if you can run a terabyte of data on 10 machines, if I have 2 terabytes of data, I should be able to run the same application on 20 machines, but without increasing the time, right? So that's called weak scaling, and MapReduce is designed to weakly scale. And lastly, it's designed to fail. That's where the commodity PC comes in, which means that if a machine fails or a disk fails or something fails, the application doesn't terminate, right? It can actually recover from a certain point in time and proceed without maybe going back an hour to when the application started and starting it from scratch, right? So these are some of the properties that MapReduce has. And just so that, meaning MapReduce itself is used as a very sort of broad term. So MapReduce itself actually refers to a programming model, right? It's like saying MapReduce is like Java, right? But Java itself has different distributions. You got a Sun distribution, or the Oracle distribution nowadays, right? And you also have things like OpenJDK, which implement the Java language, but have their own runtime implementation, right? So when you talk about MapReduce, you're talking about the programming model. When you're talking about Hadoop, you're talking about the implementation of the programming model that's available in the open source community, right? So when Google originally came up with their paper, Yahoo quickly read it and said, hey, we are doing search also. We need to do sort of page rank and so on. So let's go implement the MapReduce sort of programming model within our own sort of, for our own use. So they did that, and then they actually donated it to Apache in the open source community so that they get some credibility with and after that the whole community developed around that, right? So when you talk about MapReduce as a programming model, Hadoop is the open source implementation from Apache. And the Google file system is essentially the notion of a distributed file system that MapReduce uses. The internal version of Google is called Google File System. The public version that's part of Hadoop is called Hadoop Distributed File System. And you have some of these MapReduce implementation even available from cloud providers. Like Amazon has their own distribution of MapReduce, Azure, Microsoft has their own, and so on, right? All right, let's quickly talk about what the MapReduce programming model is about, right? So it's fairly simple in the sense that the primitives that you typically have are captured in the name. So one is a map, other is a reduce. And that's pretty much it, right? There are some sort of nuances there, but if you understand map and reduce, you can pretty much go and write your own MapReduce application, right? The map method, and this is an interface that you guys have to, like any developer of MapReduce has to implement. So the interface is given to you. The map method takes in a single key and a single value, a key value pair, right? And emits a list of key value pairs. And the list can have 0 or more key value pair outputs, right? And the reduce method, which is called after the map method finishes, takes as input a single key and a set of values associated with that key, right? And this, again, this list can have between 0 and arbitrary number of values, and it emits a list of key value pairs, okay? So one thing to note is, one thing is that the output of the map effectively goes to the reduce, right? And between the map and the reduce, which developers implement, the framework itself does a group by operation. So effectively what the framework does is, let's say you take in a key value pair, you emit a list of key value pairs. The framework looks at all the different keys, and for every key, it groups all the value associated with that particular key, right? And that grouping is actually passed to the reduce, right? So effectively, if you guys are familiar with SQL, the output of the map operation essentially goes through a group by operation, right? Where the group by key is the key that's emitted by the key field that's emitted by the map method, right? And the output of this group by is passed to the reduce, right? So the map method itself is called once for every line of input that's present in your input data, right? So we got an input data with, let's say, you've done a web crawl and you collect all this sort of text in Wikipedia. Let's say you manage to do that. And you give this to MapReduce. So every line in Wikipedia will be an input to the map method, right? And in this case, maybe the key is just the line number and the value is the actual sentence, right? And the output that you generate might, for example, be the frequency of every term or every word in that particular sentence. Maybe the appears 3 times, and appears once, maybe Wikipedia appears once, and so on, right? So the key is going to be the word, and the value is going to be the number of times the word appears, right? And then the reduce essentially takes groups by the key and gives the list of value associated with each key. But this group by operation occurs across all the sentences, right? Not just a single sentence, right? That's really where the power of MapReduce comes in, right? So the map method gets called once per line. The group by happens on the output of all the outputs from mapper. And the reduce is called once for every unique key that's present across all the outputs from the different mappers, right? So the English language has about 50,000 frequently occurring words. So if you assume that if you do a union of all the outputs from the map, you might have about 50,000 unique keys, right? So all the values associated with each of the 50,000 words is taken, and for every word, you get a list of values associated with that word. And the reduce can do its own operation and give an output here, right? So this group by operation is called shuffle, as you see over here. So you get an input. Every line is processed by the map method that you guys implement is called on every line of input independently. A group by shuffle happens. The reduced is called independently for every key values pair, and the output of the reduce goes out, right? So let's see how this works in practice, right? So you have, and let's do a simple histogram operation, right? So which is like doing a word count sort of, it's essentially like counting the frequency of numbers, right? So let's say you've got a huge corpus of data, maybe the Indian census. Maybe you've done this Indian census, you have access to the data, and you essentially want to do a histogram of, and you've got a billion lines of input, right? And you want to do a histogram of age distribution of all the Indian population, right? So this is what you do. You'd have a list of numbers which are the age, right? So every line has, every value for the map is a age value, right? And the output should essentially be bucketed, and here in this particular case, the bucket width is given to be 4, which essentially means that every bucket is going to have ages from, let's say, 0 through 3 would be in one bucket, 4 through 8 would be in another bucket, and so on, right? 4 through 7. So the map gets every line, right? And all it does is it emits as a key the bucket ID, which you simply get by dividing the age by the bucket width, right? So the value is divided by the bucket width, and the value of the key associated with the key itself is 1. And effectively you're saying that's the frequency at which this particular age appears. And since it's only looking at one age at a time, the frequency is always going to be 1. What's going to change is the bucket where that particular output goes, right? And this gets executed a billion times on a billion lines of input, right? And the output of that is going to be, if we get this graphic right, so this is how the output is going to be, right? So 7 divided by 4, when you do a floor of that, you get 1, 2 divided by 4 is 0, and you got 9 divided by 4 is 2, and so on. These are the keys, and these are the values, right? Likewise for all the lines of input that you have, right? Now the shuffle happens where you do a group by. So all the buckets with key 2 are grouped together, right? And these are the values associated with them. All of them have a 1. All the buckets with key 0 are grouped together, and all the ones with 1s are grouped together. So the count of this and the count of all of this is going to be the same, except that they've been reorganized, right? Now the reduce, all it needs to go is just add up all the values. That's it, right? So you add up for every value that you see, just keep adding that value, and all you do is emit that particular key along with the sum of all the values that you've seen, right? And this essentially gives you a histogram, essentially by sort of collecting all of these things and plotting it nicely, you would have achieved what you wanted to do, right? Any questions on this so far? I can take a pause for a minute. None? Either it's too easy or too difficult. I don't know which. All right, let's keep going. So this is, again, at the end of the day, this is just more a primer. So most of your learning is probably going to happen outside the classroom when you go to Google or when you look online at some of the MOOCs courses, or just try it out yourself, right? So internally, this is what happens, right? So every line of input actually doesn't go to the same machine, right? So that's really the power of the Hadoop framework, right? So we've got a billion lines of input. Behind the scenes, these billion lines are just arbitrarily divided, let's say into 1 lakh, a million lines each, right? Not even a million, let's say 10 million lines each, right? Which means that you'll have 100 different files, each having 10 million lines of input, right? And each of these 100 files can be given to a separate map method running on a separate machine, right? So effectively, you've got a billion lines of input, split it into 10 million chunks, spread it across 100 machines, and have map execute on each of these 100 machines, right? And even within each machine, you can have multiple mappers and so on, right? So the map method is completely parallelizable. And then the output of the mapper, again, has to be collected from across all these different machines, and that's what really the MapReduce framework does for you for free, right? It goes across the output of all these mappers from these 10 machines or 100 machines, groups all the values together, and gives the grouped result to each reducer. And the reducer, again, might be spread across, let's say we've got, for simplicity, assume that age is between 0 through 100 or 0 through 99. You've got bucket width of 4, which means you have about 25 buckets or so, right? Which means you can have up to 25 different reduce methods independently do their aggregation, right? So that, again, gives you a degree of parallelism. The degree of parallelism for the map is almost the number of lines of input that you have. And the degree of parallelism for reduce is the number of unique keys that the mapper generates, right? So maybe you have 100 mapper machines, you've got 25 reducer machines, and they all do the aggregation in parallel, and you get the output over here. And the shuffle and sort happens between the map and the reduce in a distributed fashion by the framework, right? And again, this shows you that you can have different mappers per machine, mappers themselves distribute across machines. And since the map, all the mappers have to complete before the reduce starts, right? It means that the reduce methods can run on the same machine as the mapper. That way you don't have to have 125 machines. You just need 100 machines, and for the map phase, all 100 are useful. And for the reduce phase, only 25 of them are useful, right? All right, so this is pretty much saying the same. Typically, the machines holding these original data sets that are distributed across are called the data nodes. And the machines running the map and the reduce methods are called task nodes, task trackers or task nodes. And both of these actually overlap. So, but they don't necessarily have to overlap. The data itself could be distributed in a different subset of machines from the machines on which the map and the reduce methods run. But ideally, both have to be on the same machine for having good performance, right? All right, so let me actually skip through. I'm just going to skip page 9 because that's going to take a little bit of time to explain, but you guys can go and read it on your own. But let's briefly get into 2 other topics, maybe 10 minutes each in the time that we have. So one is on graph processing, right? So MapReduce is great for text data or like essentially tuple data, things that you have a lot of lines of data that you want to process and that you want to process completely independently because there's no relationship between the census entry for one person and another person, right? You can sort of deal with them independently until you come to the aggregation phase, right? But not every data set has the luxury of being processed independently, right? Oftentimes, complex data sets or linked data like graphs, like the social network, there's a lot of dependency that's built into the structure of the data itself, right? And that makes it a bit more challenging to deal with, right? Again, you see graphs everywhere, though you might not realize that it's a sort of graph data structure, meaning social networks, the web network, the internet itself are all graphs. And you have the graph algorithms you guys have learned are equally applicable over here. Like PageRank is actually used on top of a web graph to actually rank various vertices or web pages. Within the graph, you can use things like centrality measures and so on for seeing who are the most important people. Or to suggest people, for example, Facebook comes and says, hey, maybe these people are friends with you. They're effectively doing a graph algorithm to see who are sort of common people that you and your friends are friends with. And if you aren't friends with someone that all your friends are friends with, it probably suggests that using a graph algorithm, right? Road networks, power grids, these are all examples of graphs also. I mean, things like shortest path, Dijkstra's are equally well applicable. When you use Google Map, effectively it's running a form of Dijkstra's behind the scenes. For giving you directions. And graph algorithms are complex. So any of you who remember your data structures course and the complexity analysis know that some of these graph algorithms can be E times V, V square, V cube, and so on. And we are looking at graphs that have millions of vertices, right? Facebook has 1 billion vertex, right? And you do a V cube or a V square on that, bets are off. You're not going to be able to complete it in this decade, right? So you need to be able to sort of deal with the complexity of graph algorithms, especially when you're looking at large-scale graphs, right? Road networks can have millions of vertices also if you're looking at the entire country and so on. I think that you had a talk on neuroscience, right, earlier on. Brain networks, right? Meaning, think about that. The whole brain is sort of one of the most complex networks out there, and we're slowly getting hold of data that actually scans the entire brain. But now when you want to do analysis on that, if you want to simulate a human brain in a computer, right, that's going to be exceedingly complex, not just because of the size of the graph, but also because of the complexity of the algorithms, right? So these are all fairly important challenges, and doing sort of parallel graph processing or scalable graph processing is challenged, right? And while there has been some work on actually using MapReduce for graph algorithm, because at the end of the day, PageRank is actually a graph algorithm, right? That's running on top of the web graph of web pages and links between the web pages. But you actually have to run multiple iterations of map and reduce, because of the way PageRank works. It's an iterative algorithm, which means that every time you run an iteration, you're running a MapReduce job. And it takes anywhere from a few seconds to a minute to run a MapReduce job, just because of the overhead associated with launching it, right? And if you do it 30 times or 50 times, you've just lost 30 minutes just in running it, let alone just in launching it, right? So Google, again, this is what I think a few years, about 5-6 years back, realized that their own contribution MapReduce was not good enough for graphs, and they came up with a sort of alternative called Pregal, which is intended for graph analysis, right? And they essentially leveraged work from the 1990s in terms of how the execution itself works, and this is called the bulk synchronous parallel model. And the high-level idea is that oftentimes when you take applications, right, even for example MapReduce, you go through a computation phase, and then you go through a data exchange phase, right? So for example, in MapReduce, the computation phase is the map first. Then you have this data exchange in terms of shuffle and sorting that takes place. And then the reduce receives the data, and the reduce, which is another computation phase, happens. And the reduce emits output, right? So you got a communication phase, computation phase, computation phase. And this BSP model generalizes that. It essentially says any parallel application is a series of these super steps, where every super step has parallel computation taking place. And once all the computation is completed, you start the communication phase where all of them are communicating. And once communication completes, you start the computation phase and so on, right? So that's sort of the big picture BSP model. And one of the advantages of that is that it's in networking, right? It's actually costly to send small packets, right? If you look at the bandwidth of sending a very small file, you guys can do this test at your home. If you do a speed test with a very small file, the bandwidth is going to be fairly low, the effective bandwidth, right? But if you take a large file, think about transferring 1,000 small files versus one big movie, right? The bandwidth that you get from the big movie is actually going to be much more, right? And that's what this tries to leverage. So by making sure that everyone does communication at the same time, you're batching all the communication into one large communication, rather than having 1,000 small communication, right? So that essentially allows you to leverage the overall bandwidth of the network by having these kinds of execution. So this is an example of how maybe different machines, they're all doing computation in parallel. Each one takes a different amount of time to finish their computation. And once they finish their computation, they all start their communication phase, which is shown by these arrows. And once everyone finishes their communication, then you have a barrier synchronization, and then you start the computation of these different machines for the next super step. Right? This is sort of the big picture of how a BSP model happens. Right? So when you map this to doing applications on top of graphs, right? So here, while map and reduce work on tuples, which is why you have the key value pair, which is like a tuple, right? So in Vertex Centric Programming Model, so you have the notion of vertices being your unit of computation, or vertices being the ones that are performing computation in place, and the vertices can actually do various activities, like exchange messages with other vertices, or do computation on top of their own value, and so on, right? So vertices know about their own value, right? For example, if it's, it might be the label of a particular vertex, or it might be some other property of that particular vertex, and they know about their outgoing edges. So if it's a road network, you might know what the outgoing edge weight is for all your outgoing edges. But that's all every vertex knows, right? And using this information, they all collaboratively perform graph algorithms, right? And the execution itself is a series of iterations, right? And for every iteration in the compute phase, all that the vertex does is it invokes a compute method. So this is like the equivalent of the map or the reduce. You implement a compute logic, and for every super step during the compute phase, the vertex just calls the compute method on its own state. And the state that it has access to is its own value and the outgoing edges, right? And in addition, as part of the compute method that you would implement, you can send messages to your neighbors, right, neighboring vertices, which would actually be communicated as part of the communication phase and available as part of the next super step, right? So though you're sort of sending a message, you're sending it asynchronously, and it won't be received immediately by your neighbors, right? So you can send messages which will be available in the next super step S+1, or you can also receive messages that have come from the previous super step. So you could have received messages from super step S-1, process those messages in the current super step S, and send messages to your neighbors that arrive at the neighbors in super step S+1 for them to start computing, right? And vertices can also modify their own state or the state of the outgoing vertices. So this is pretty much all that happens. This is essentially a big while true loop, where within the loop, all you do is receive message, do computation, potentially generate message, and that's it, right? Very simple model. It's even more simpler than the MapReduce phase, where there at least you got the map and reduce logic, two different logic. Here, this is one logic. That's called iteratively, right? So, again, one of the advantages of having such simple, one might wonder, right? So, meaning things like Java or C, C#, these are very powerful languages, right? So why not use those, right? One of the challenges with those is actually writing parallel applications, right? If you want to actually, meaning from your OS topic, right? You know how difficult it is to do a reader-writer, where you got one reader and one writer, right? And here you have 100 or 1,000 readers and 1,000 writers, right? How do you coordinate across them? Especially when they're not even the same machine. They're across 10 different machines or 100 different machines, right? So distributed coordination and synchronization is exceedingly difficult as your program becomes more complex, right? As a result of that, by mapping your application to such programming, distributed programming models, the programming model give you the guarantee that you won't have deadlocks or race condition, right? Internally, they ensure that it's a lock-free model. But the consequence of that is the programming model is itself simple, which means that if you have a complex algorithm, you really have to think hard to see how that would fit within the programming model, right? So here again, the Vertex Centric model has just a single compute method. I'm just going to skip forward. Giraffe is essentially the implementation of Google's Pregel, just like you have the MapReduce and Hadoop. This is like Pregel and Giraffe, the equivalent. Again, developed by Yahoo, donated to the community. Yahoo is good at that. And effectively what happens is when you give a big graph to, let's say, Giraffe, it takes the graph, distributes the vertices across arbitrary number of machines, let's say 10 machines. And on each machine, it just loads all the vertices into memory. And for every vertex, when you start an application, and we look at an example application in the next slide, it just takes the compute method, runs it on all its vertices in parallel, because there is no dependency between vertices in a single superstep. The dependency comes from the communication across different supersteps, which means if you've got 1,000,000 vertices in a particular machine, those 1,000,000 vertices can execute in parallel, right? Just as in the map method, we've got 1,000,000 rows. You can execute all those 1,000,000 rows in parallel on different map threads or map logic blocks. So it runs a computation every vertex in parallel, and it essentially runs, that's the computation communication. But when do you stop? Right? Because in the MapReduce it was clear. You run the map once, you run the reduce once, you're done. Right? Here you have many super steps, but if it's a while true loop, when do you break? Right? So over here, and this again is a consequence of distributed programming, oftentimes you don't, so when you stop is not just something that's previously defined, saying that, hey, you have to run for 10 iterations, right? Sometimes this has to come through distributed coordination. So you need to know some information about all the vertices in order to decide if they are done or not. So in order to make this easier, and this is something that you get for free from the programming model, every vertex can, at the end of a superstep, it has a vote saying that whether it's voting to halt or it's voting to continue, right? And the requirement is that if all the vertices vote to halt, then you won't have any subsequent supersteps, right? But here again, you might have a scenario where a vertex votes to halt, but it actually sent a message to someone else. That will be received in the next superstep, right? And maybe the one who's going to be receiving it thinks that they are done because they don't have anything more to do, but they don't know about the message that's coming into them, right? So the requirement is that in a superstep, all the vertices vote to halt, and there is no message in flight between one superstep and the other superstep. As long as both these conditions are met, the application terminates in that particular superstep, right? But even if one of them is not met, the vertex receiving a message, even if it's voted to halt in the previous superstep, it's woken up again, and it said, hey, here is a new message from your neighbor, start processing that, okay? So let's look at a simple example. So this is a graph of just 4 vertices. The arrows are directed edges between them. And I've shown 2 different boxes just to indicate that these might be in 2 different machines, right? So each of those boxes are a different machine. Again, this is a trivial example, right? You can sort of multiply this by 1,000,000 and you'd have 4 million vertices, and this equally applies, right? And here the goal of this algorithm is simple, right? We're going to use a vertex-centric model, right, to decide which vertex has the largest value, right? So, meaning you can look at this and say, hey, 6 is the largest value, right? So, but all the vertices should realize that 6 is the largest value, and we want to do this in a distributed way. And it's great for you to look at this 6 and say, hey, this is the largest with 4 vertices. But if you've got 40 million vertices, it's not going to be so easy, right? And here again, we want to use a graph property. It's not like you're given a table of 40 million values and just scan through it and do a linear scan and do that, right? This is a graph, so you actually have to go using the graph property, right? The logic is fairly simple. So this is the vertical axis is going to be the different supersteps that I'm going to indicate. So in every superstep, the compute logic is simple. You just look at your own value, your current value. You look at an incoming messages value. Whichever is larger, you update your value to that. And if you updated your value, you send that value to your neighbors. That's it, right? So in the very first superstep, all of them, they don't have any incoming messages, so they just send their own current value to all their neighbors. 3 sends its value to its neighbor 6. 6 sends its value to its neighbor 3 and 1, because it's connected to them. 2 sends its value 2 to 6 and 1, and 1 sends its value to vertex 2, right? Computation phase is over, the communication phase starts, all the messages are delivered to these 4 other vertices, and in the next phase, every vertex checks its current value with the incoming messages value. Whichever is higher, it updates itself. So since 3 received a value from 6, 3 becomes 6. 6 didn't receive any value that was higher than itself. And if it doesn't receive a value higher than itself, it votes to halt, right? So 6 votes to halt, it becomes blue. Now 2 received a message from 1, right? And since 1 is smaller than 2, 2 thinks it's done and 2 votes to halt. And 1 receives a message from 6, so it updates itself. And those vertices that haven't voted to halt, which means their values have been updated to a larger value, they actually send their values again to their neighbors, right? So the first and the last vertices have values updated, so they send their new value 6 to their neighbors, right? So these 2 go here, and since the second vertex 6 receives a value it already knows about, it wakes up because it's got a new message. It checks that its value is the same, so it hasn't changed, and it votes to halt and goes back to sleep again, right? 2, on the other hand, has voted to halt, but it receives a value 6. So it wakes up, checks its value against 6, and it realizes, hey, I have a new value, so I actually have to sort of propagate this. So 2 becomes active and sends its updated value to the neighbor, right? So this happens, it against only 2 sends a value out, its new value is 6. Both of them, the other 2, they wake up, check their value, see that it hasn't changed, go back to voting to halt. And since the third vertex doesn't receive any incoming messages, it votes to halt. Now everyone's voted to halt, no outgoing message, the application terminates, right? All right, so just to sort of quickly give the, if you want to look at the pseudocode, it's just about 10 lines of code, right? Most of these algorithms, right? So they're fairly simple in the number of lines of code that you have to write. So in every superstep, you check if the superstep is 1, in which case you send your value to all your neighbors by setting a flag to change. If not, for every incoming message, you check the message against your current value. If the current value is less than the incoming message's value, update yourself and set the change flag to true. And if your value has changed, propagate the message to all your neighbors. If the value is not changed, vote to halt, right? So this compute method runs in parallel across all the millions of vertices that you have, and it iterates till everyone's voted to halt, no new messages. And at the end of the application, every vertex is labeled with the value of the largest vertex out there, okay? All right, so I'm going to sort of try a miracle and squeeze in one more topic in the next 5 minutes, if I can. And again, I'll be very brief about that. You can sort of read up about it later on. But I want to sort of briefly go about dealing with high velocity data. Meaning Aadhaar was an example. Internet of Things is a huge thing that's coming on that's going to be generating a lot of data that you have to deal with. So high velocity data is getting exceedingly important. And the key sort of challenges over here is the need to do low latency processing. So when you get a piece of information, right, you have to immediately process it, analyze it, make a decision, and sort of push it out in terms of a decision that you've made, right? So the questions become, how do you actually move data from the source to the processing unit? So if, let's say, your device is there, let's say on the edge, which means it's away from the cloud, maybe on the campus or someplace like that. The processing is happening in the cloud. How do you actually get the data from here to there and back quickly? Because there's a latency involved in this round trip time. And if you're generating a lot of data, this latency can kill you, right? Once you get the data, let's say into your big data platform, how do you process it quickly and get a result out? If you look at Giraffe and Hadoop, these take between seconds to minutes to process large data sets, right? But in stream processing or fast data processing, we are looking at low latency processing, which means you look at small pieces of data, but rapidly process them and give a result back, right? It's the difference between reading a tweet and reading a newspaper, right? You can read a tweet in a second, process it, and you're done. Reading a newspaper takes longer, or a novel, much less, right? So low latency is the key over here. And also, how do you actually store data over a long period of time and analyze that? That's a whole different deal, right? This is again the sort of picture from Aadhaar, but now you also have not just the incoming data rate for acquiring or sort of registering new residents, which is over here. X-axis is time of the day, y-axis is the rate in thousands. So the peak rate is about 70,000 people registered in 1 hour across India, right? So just so that you have the units, right? And in terms of, that's the example of other authentications that are taking place. And at 10 o'clock, you're authenticating 2 million people within a 1 hour period, right? And these are people who come, give their attendance in their door and sort of go in. So you're looking at very high speed data that's coming in, and they have to sort of immediately give a green or a red saying that, hey, your authentication has been registered, right? All right, so again, IoT is another example. So here on campus, we have an IoT project for actually doing smart water management. We have a bunch of wireless sensor network, Raspberry Pi modes that actually do analysis, push data to the cloud, do stream processing and so on, actually take decisions on, should you actually turn on the pump, right? Or should you actually, what's the quality of data, right? Or what's the water footprint of each individual on campus, right? These are kinds of things that happen in real time as you get data from the sensors on top of water tanks and so on, or water pipes. So these are examples of fast data that come in. So the key is low latency processing and stream processing, and event processing are two sort of classes of such fast data analysis. The distinction being that stream processing looks at messages as opaque objects, while event processing looks at messages as tuples, which actually have a schema, right? So a subtle distinction over here. And typically these are composed as data flows, which means that you have these series of task blocks. It's not like you just have a map and a reduce or just a compute method that keeps iterating over. These can be fairly sophisticated. So these are sort of building blocks that you essentially compose. Each box is a different logic that you provide. The arrows actually say that, hey, the input stream, the output stream from one task has to be delivered to the input of a different task. So if you generate a series of tuple, they're continuously going to sort of be acquired, processed, and emitted, right? Without any kind of synchronization like you see in Map or MapReduce or in Giraffe, right? And again, that's actually a sort of realistic scenario for that Aadhaar can potentially use for acquiring users in terms of the different kinds of checks that they do as they get people registered, right? And you have a bunch of sort of open source tools and programming models, just like unlike MapReduce, which is sort of almost like a monopoly. Here are several others, but Apache Storm, which came out of Twitter, or they do real-time processing of tweets very frequently. That's actually fairly popular. And these again scale across different machines. So for example, each of the logic blocks that you see over here could be running on different machines. And you can have 100 copies of each of these logic blocks that are spread across the machines. But overall, they coordinate with each other such that if an event is generated comes into the input, which is called a spout, it actually goes through all the different blocks and is processed and is emitted out as a part of that, right? So, all right, so let me just, you can read up about Storm offline. So you have spouts that emit streams of tuple, you have boards that take in different streams of tuple, do some user-defined logic, and emit 0 or more tuples as the output. And all of these happen on a per tuple basis. You don't have to wait for a big chunk of data to come. These happen in real time as data comes in. And you can compose these spouts and bolts together in the form of these data flow topologies, and then sort of design your application in such a way. And this is an example, for example, this is an example from within Twitter, where they actually do something called a reach count, where they find out how far a particular tweet will propagate for every person, depending on their connectivity and so on. So they get input from every tweeter, look up their followers, and look at the count of distinct followers for each tweeter, and that sort of gives you the reach for every person. This happens in real time as people add or subscribe or sort of, what do you call that, follow or unfollow people. These take place, right? This is an example of a real-time execution, right? So just to quickly summarize, we saw about big data as a whole and different motivations for that, and 3 different categories of scalable platforms. MapReduce for dealing with large volumes of data, Giraffe for looking at large-scale graph analytics, and Storm for doing low latency stream processing, right? So that you get an input and output and the whole thing gets done for an event in maybe sub-second, right? And all of these fall in the bigger context of big data stacks. So if you take Giraffe, it's actually built on top of Hadoop, right? Though I didn't sort of get into that. So Giraffe application, right, effectively is a MapReduce, it's a map-only Hadoop application, where you don't really use a reduce phase, but you only have the map phase, and the map phase keeps running forever, right? Likewise, there are some sort of Hadoop ecosystem objects like Zookeeper and so on that's being used by Storm, right? So behind the scenes, a lot of these things are layered on top of each other, and they actually have dependencies on each other, because it's difficult to build these large-scale systems. And if someone solved the problem for you, you might as well take a piece of their solution and reuse it rather than reinvent yours, right? So thinking about stacks is useful. Again, the data characteristics are important, be it so the structure of the graph, power law, social network graphs are very different from spatial transportation graph, might be very different from gene or neuroscience graph. So understanding your data is very important. And look, understanding infrastructure is equally important. So most of the big data platforms are designed for commodity clusters or clouds, but you also have those that are customized for GPUs, right? Or those that might really work with big memory machines, right? So picking the right platform for the infrastructure that you have access to is important. And designing distributed algorithms, meaning the algorithms that you saw were fairly simple, right? They are almost deceptively simple, right? Whether it's histogram or sort of max count and so on. But designing more complex algorithm using these simple primitives can become very difficult, right? And that's really where some of the open research problems really are, right? So how can you actually do, let's say, all path shortest path, or some kind of a min-span tree, using a vertex centric model, right? Can you do it at all, right? So solving those can have a big impact. There's a bunch of interesting systems issue in terms of how do you optimize the execution of these big data platforms on these clouds, how do you deal with reliability, performance, low latency, how do you execute across a Raspberry Pi and the cloud simultaneously so that you reduce the latency of data round trip and so on. There's a bunch of interesting stuff to deal with over there. So it's an exciting space. So, and for those who are interested in systems research, it's a great space to be in. So go out there, try it out, whether it's Hadoop or Giraffe or Storm or your favorite big data platform. Most of these you can actually run off your laptop just to get a feel for it. You don't need a big cluster. That's one of the big advantages. All of them have a single machine installation available with a bunch of samples, so you can literally try it out this afternoon and get it up and running, okay? All right, so I'll leave it at that and maybe spend a minute or two for questions from you guys to me, and then we'll probably do the other way around, all right? Most of these sort of slides that I used are actually from a course that I teach. So the webpage for the course is out there. It's Scalable System for Data Science. That's the name of the course. All these slides, maybe 30 odd slide decks are out there. Meaning from 20 odd lectures are out there online. So if you're interested in any of these topics, you can go read them up and sort of, in addition to any online resources that you might find. And meaning I have to do this pitch. So I'm from the Department of Computation and Data Science. So those of you guys who are interested in, especially I work on distributed systems, so the systems aspect of data science. So if you guys are interested in doing a master's or a PhD, we more than welcome you. So we just look for a lot of enthusiasm. Good programming skills always helps. And typically, at least for a few of our faculty there, we look for computer science students with sort of these skills. So I think by end of this year, you can sort of take your GATE exam and send in your application, and we'll be looking forward to seeing you next admission cycle. All right, so I'll take questions maybe for a couple of minutes now. Questions? No? All right, so let me try a question, just to see how many of you guys were receptive, right? So let's try this. So who developed Hadoop? Okay, good. So I think I overemphasized that in my talk, knowing that this question was coming, right? But so Google came up with the original MapReduce model. Yahoo developed the first version of Hadoop and contributed to the community, right? So, but for the past 4 or 5 years, it's actually been the open source Apache community that's been developing Hadoop. So there's a little bit of a sort of subtleties allowed there. So Yahoo is true in the first version, and subsequently Apache is developing it. And again, a lot of people contribute to MapReduce. So the answer is actually much more broader than this, because you guys could go sort of see some interesting feature you want to add to Hadoop, and you could commit to the Hadoop code base also. So you guys could be developers of Hadoop too, right? Let's try another one. So how many super steps do Giraffe applications run for? 11, okay, I got 11 here. Any bigger number? Right, so I think you guys broadly got it. So the number of superstep is not fixed, right? So it's going to be application specific, and even if it's application specific, since it's a distributed application, oftentimes the number of supersteps you run for is dependent on probably the graph property. So for example, in the example that we saw, it ran for about 4 supersteps or so. But if I give a larger graph to the same algorithm, it might take 10 supersteps to run. So the number of supersteps depends on when all the vertices decide to vote to halt and don't generate any messages, right? So, and this is necessary for distributed coordination. But that said, sometimes for algorithms like PageRank, which unfortunately we didn't get time to go into, the rule of thumb is that you actually run it for 30 iterations or so, right? So there are some algorithms where you know a priori how many iterations to run it for, where there is no distributed coordination required. In such algorithms, every vertex essentially checks the current superstep number, and when it reaches 30, all of them vote to halt, and they don't generate any messages, right? So it's also possible to program fixed number of iterations or fixed number of supersteps into the Pregel model, and PageRank is one example of that, right? All right, let's try one last one. This is a simple one. So which ones get mapped to which one, right? Streaming data flow. So what do you think first of all, so what's the first column about? What's the first, second, and column? What are the categories? The first is the programming model, right? The second is the platform or the implementation of the runtime implementation of the programming model. And the third one is the type or the characteristic of the data which these platforms or programming models are better suited for. So streaming data flow would be Storm, which does high velocity data, right? So MapReduce is implemented by Hadoop and does volume data, and Vertex Centric models are for Giraffe, which is sort of variety of data. Okay? All right, looks like everyone was a big. So if you want to give prizes, you have to go to everyone, like lunch. All right, so if you have any questions, I can take it for a minute, or if not, we can wrap it up here. Great, thank you.
Okay, thanks Professor Yogesh for the absolutely interesting, absolutely amazingly intriguing talk. And so a couple of announcements. Try to come back by 11:25 because we have attendance sheet. We'll be distributing it, and you have to check the name.